Welcome to the next lecture. So today we are going to look at the scalar, vector and tensor perturbations. Scalar, vector and tensor perturbations of the metric tensor in the Fourier space. We will continue from where we left off last time. Last time we saw how to express a scalar component in how to expand a scalar component in Fourier space, and we looked at like you can expand scalar components. We looked at three mechanisms. One is the expansion of a scalar component, which was a scalar perturbation, which is originally a scalar perturbation. For example, like metric tensor, if you look at the metric tensor perturbations. In the metric tensor perturbations, as we have seen in the previous lectures, that we have scalar components, A, D, and from the vector bi we derived another scalar component b, and from the tensor eij we extract another scalar component e. So this one is extracted from vector bi, this one is extracted from tensor eij, and then we have a vector which is extracted from, which is the leftover part of bi after you extract b from bi, and that is a divergence free part of bi. So bi, you can say v, and then we extract another divergence free vector from eij, we can call it ei. So then we have the leftover tensor after you extract a scalar and a vector. This is extracted from this part, this is extracted from eij vector, and this tensor is extracted from b, is extracted from bi scalar, this, and the leftover tensor is eij tensor. Yeah, so we are like original perturbation was bi vector, we split it into bi scalar, bi vector, and original perturbation was eij tensor, we split it into eij scalar, eij vector, eij tensor. Eij scalar gives us e, eijv gives us ei, and the leftover part is etij, and then we have seen that a is expanded, a and d, they both are expanded like this, whereas this is a function of eta, this is a function of x alpha, and we have k here. So d is also expanded in the similar manner, but for b we took a slightly different approach for the expansion. So this is k coefficient. We said that we would expand b, we will write b like this, bk. Again, Fourier coefficients are functions of eta only, so it is a function of eta, and I kx sum over all k modes, and so for the vector, for the scalar which is extracted from tensor, we will divide it by k square. Again we are doing this so that we can keep the dimension of B same as the original vector Bi, dimension of Ek same as the dimension of Eij. Only for that reason we are dividing by these factors. And then we have if it is a normal vector like BV, you would expand it just normally without any factor. BVKEIKX. But if it is a vector extracted from a tensor, if it is a vector which is extracted from a tensor, you would expand it as, and all of this we saw in the last lecture. So if you have a vector EI which is extracted from a tensor, you would expand it as EI K over K. This. Okay, and then we also saw in previous lectures that there are constraints on these perturbations. The constraints are that this is 0, which gives us constraint delta ij ei delta ij b ij is 0. Then we have constraint on ei, delta of vector e is 0. This gives us sorry, what is this? Bi comma j. Bi comma j. Okay, so delta ij ei comma j is 0. Then we have constraint that Eij t is traceless. Eij t is traceless. This gives us this is equal to 0. And then we have another constraint that Etij is also transverse, so that we can get the gravitational wave components. And for that we have delta I k e t ij comma k is equal to 0. Now before we go ahead and write the metric perturbations in the Fourier space, let us first write Let us first write these conditions, these constraints in the Fourier space. So I would like to write all of these constraints one by one in the Fourier space. How many constraints I have here? All of these expressions. Let's first start with this expression. How does this would appear in the Fourier space? Bij, which is basically del dot bv is equal to 0. And we have seen earlier that in Fourier space, when you write del dot, did we do this? No, we did not do this. Okay. So del dot bv is basically what? Del of any vector, and this applies to any vectors. So we have del by del x bx. This will be b sorry, let us consider any vector f. F is any vector, and I can write this as fk eikx sum over k. Del dot f will be this is f, so I can write this as fk, and when we do del dot, so sorry, this would be because this is a vector, I need to do k1 and fk one component plus k2 fk2 component, or yeah, so plus k3 fk 3 component ei k dot x. This is equal to, you can say this becomes k dot fk ei kx, and this is equal to 0. This implies, so basically let's first of all note that del dot f in Fourier space, this becomes I k dot f, and if we remove the, if we get rid of this subscript k, this becomes a k dot f, and in Fourier space the subscript is implied on the perturbation. So del dot f becomes iota k dot f. So if this is 0, if del dot bv is 0, that means in Fourier space k dot bv is 0. So we have k dot bv is 0. Similarly, we have discussed in our previous lectures that EI is also divergenceless, and therefore k dot E is also 0. One thing I also want to mention that you may like to write this in index notation. If you want to write this in index notation, you would like to write this as K and F, Ki and Fj and delta Ij. Yeah. This, don't confuse this with index. This is this I is iota and this Ij are index delta Ij. So this is how would you write this dot product in the Fourier space using the index notation. So we have k dot bb0, or in other words delta Ij J is 0. K dot E is 0. In other words, delta missing something here. I'm missing something here. 1 second. This means that k dot bv is equal to 0. This means delta Ij ki bv j is 0, and this here it means delta Ij ki Ej is equal to 0, and then Eij is traceless. This gives us traceless condition gives us delta Ij, sorry, not E but E T, because we split T into 3 parts, and now ET part is traceless, so this gives us delta Ij ET Ij is 0. And also we have another condition which is gives us this delta Ik Et Ijk is traverse condition is delta Ik Et I comma j in terms of its Fourier components. When you are taking derivative of j, that means you are bringing what did I do here? Did I make a mistake? I think this would be Et I j comma k is equal to 0. And what is this etij comma k? This is if you expand etij in terms of Fourier components, etij k ij component of k vector and eikx. So when we take its derivative, and then ik component will come in front, ik component, k component, tkij. This comes here. So if we say that etij comma k, tij comma k, if we say that this is equal to 0, this means that this is equal to 0. In other words, we have delta ik not this equal to 0, but this whole thing is equal to 0, including delta ik. So we have delta ik and then k et. I'm dropping the subscript k, etij is equal to 0. So we have written all the constraints in Fourier space using index notation. So this is what we have done. We have written all the constraints in Fourier space using index notation. Now next we would like to see how we can put all these perturbations in the metric tensor, in the perturbed metric tensor. So we have delta g mu nu. This is the perturbation in the metric tensor, and once we put all of these components, we can separate the scalar part. So this has the scalar part and this has the perturbations which contain the vector part, and then there is delta g mu nu which contains the tensor part. So let us now in order to see this separation, we want to orient our k-axis. So we want to orient our z-axis because now we are going to look at a k mode. So we will look at all the perturbations in the Fourier space. We will look at all the perturbations in the Fourier space, and we will look at one arbitrary k mode. So for any k mode, for an arbitrary k mode, let us write delta g mu nu for any arbitrary k mode. Now let's orient our z-axis parallel to k mode, parallel to vector k, wave vector k. So I am going to orient, because I can orient x, y, z in any manner I like. So I would like to orient my z-axis parallel to k and then I would see what happens. So let us do this arrangement that we have oriented our z-axis parallel to k. Then k is equal to 0, 0, k. These are the components of k vector. And what is B S vector going to look like? So we have seen that BS vector, following our convention, in our convention we said that we will adopt this convention in which potential W is expanded like this, and the scalar and then the scalar will be written like this. So following this convention, the potential W will be expanded, like potential W will be just the potential W in the K space. Potential W potential W will be expanded like this in the K space, like this. Yeah. And potential scale and this curl free vectors BS will be expanded according to this minus I WK over K minus I BK over K What is the mistake here? Because WS is scalar, so we should have a scalar here. Sorry, WS is vector, we should have a vector here. And where is the vector part gone? Yeah, so WKS is BK over K. So BK over K. Yeah. So this vector, this should be vector K here. K here. This should be K. So the scalar part can be, the scalar vector will be written as, if it is, in K space, this is in K space. In K space, this will be written as minus I B. I'm dropping the subscript K because we are writing all the perturbations in K space. And this is B. B. So I'm dropping the subscript k. So this is minus IB IB over k. So this is the scalar vector in k space. Bs in k space. Vector Bs in k space. Curl free vector in k space. Now, because we are, you may also say that this is equal to unit vector k. Unit vector k. So vector Bs in k space. Vector Bs in k space is equal to minus IBK, and this is equal to, because k is aligned with the z-axis, so it has x component 0, y component 0, and z component is minus IB. Okay, so we got Bs. Now let us write BV. BV is note that k dot BV is 0. K dot BV is 0. And k is along z-axis. It is along z-axis. Therefore, BV has only two components. Vector BV has, BV has only two components. BV I BV 1, BV 2, and then third component is 0. And that's because our choice of axis. We have aligned z-axis parallel to k-axis. Okay. So B scalar we figured out, B vector we figured out, and then next is we want to figure out Eij scalar. In one of our previous lectures, we have seen what Eij scalar looks like. This is Eij scalar, and this is what we have seen in our previous lecture, one of our previous lectures. Eij scalar is E Ij minus scalar Ij minus let's see if we can copy this. Yeah, so this is Eij scalar. How can we write this in the index notation in Fourier space? Fourier space and index notation. how can we write this? Let's do that first. So this will become, when we are differentiating with I and j, this will become EIJS in Fourier space using index notation. Ki will come here, kj will come here, and 2 iotas will come. So this will be minus ki kj. And this is this. Sorry. This has to be EKL. Yeah. So what is this? This is basically the trace part, and yeah, this would stay as it is. In the K space. Sorry, this is not, 1 second. I made a mistake here. This is KL. Yeah. So delta Ij, delta KL, and here it will be so we have iota square will come. This will make it plus, and then we have KK will come, and then KL will come, and then we'll have EKL. Right. So next, let's see. Sorry, when we are differentiating this twice, yeah, so this will not be here. This is not here. Yeah. Okay. So this is what we get. Fourier space and index notation. Right. Now let us write, see what components are there for the because only K3 because K1 is 0 because of our orientation of K along Z axis, and K3 is 1. So that means that Ki is equal to delta I3 or if you like you can write it like this, delta I yeah, simple, delta I3. So when 3 is equal, when I is equal to 3, it is 1, otherwise it is 0. Perfect. So I can write EIJS as minus delta I3 delta J3, and I will take out E, or we can leave it like this. E plus 1 by 3 delta Ij delta KL. KK is delta K3 delta L3 E. Okay, what does this become? Minus delta I3 delta J3 E plus, now this becomes delta Ij delta KL, okay, K3 and L3. So this would make it delta 3 is equal to 1, right? So when you contract here, yeah, so this will become 1. So we get 1 by 3 delta Ij E. And now we are in the, remember that we are in the Fourier space. So I can split this EIJS matrix into two parts. This part is simple. This part is going to give me E, or you can say E by 3, E by 3, E by 3, 0, 0, 0, 0, 0, 0. And this part is going to give me only when I is 3 and j is equal to 3, I will get E. So that means only when I3, that means it is going to give me this. Okay, so I got Eij scalar. So Eij scalar gives me E by 3, E by 3 minus E plus E by 3 minus 2 E by 3. And note that this is traceless. Now let us see what do I get for Eij vector in the Fourier space. So what is Eij vector? It is half Ei comma j plus Ej comma I, and in the Fourier space I will get, in Fourier space I am going to get Eijv is equal to half iota is going to come in front, so I will have iota in front. Yeah, so this will be kj ei plus ki ej. And what is kj? Kj is delta j3. This is equal to delta j3 ei plus delta I3 Ej. So Eij vector is going to give me which component will survive? One component will be when I is 3, j is 3, sorry, I is 3, when I is 3, I get ej. Yeah, so when I is 3, yeah, when I is 3, I get delta J3 EI plus, sorry, so I get delta J3 E3, yeah, and what is delta J3, okay, plus EJ. So this gives me that E3 1 so I get E3 1 component is equal to I by 2 when j is 1, this is 0, and this will be E1. Okay, E3 2 is I by 2 E2. E3 3 is equal to I by 2. 3 3 is 1. E3 plus E3. E3 plus E3 is 2 E3. So I will get I E3. Yeah, and because of the symmetric nature, this is same as E23, same as E23, and this is same as E13. E13. Another thing we would like to see is, let us apply the constraint here. When we apply the constraint on EV, on vector E, so we have this constraint, del dot EV is equal to 0. Sorry, K dot, yeah, in K space it is K dot EV is equal to 0. So when we apply that constraint, K dot EV, this would give us K I yeah, basically this thing. Basically it says according to this K1 E1 plus K2 E2 plus K3 E3 is equal to 0. Since K1 is 0, K2 is 0, K3 E3 equal to 0 means E3 is equal to 0. So we have E vector 3 1 is equal to iota by 2 E1 3 2 is equal to iota by 2 E2. Sorry, I need to make a correction in one of my previous lectures. I said that EIJV is equal to half EI. This according to the convention which I have seen in Helsinki notes. Here it should be minus 1 by 2. So it's just a convention for some maybe mathematical convenience, and we'll see. So we need to have minus sign everywhere here. Minus sign everywhere. Minus sign. So this is this. And again by symmetry, because EV is symmetrical and traceless. So we can write that this EV IJ is equal to, we'll use the symmetry and traceless also. So this is 0 0 0. We only have 3 1 component. 3 1 component is minus I E1 by 2. Did I make any mistake here, or is it all good? Sorry, I want to make another correction, that as per the convention which we are using, we are, instead of E, we are using E by K square. E by K square. Yeah. It won't make any difference here, but still, you know, E by K square, E by K square, E by K square, E by K square, and also I made another stupidity here, that K vector K is aligned along Z axis, but that doesn't mean that K3 is 1. It's not a unit vector. It has the magnitude of K. So this is K and then this is K. So which means this will be K here and K here, and this will be K here and K here. So K square will cancel. Final expression is the right. Yeah, this makes sense now. Similarly here, when we are writing it in the Fourier space, this EI is as per the convention. this is this, and here then we have yeah, this is correct, because this will become delta J3K, KK will cancel. This is good. Okay. So we have minus iota E1 by 2, iota E1 by 2, and minus iota E2 by 2, minus iota E2 by 2. And this becomes minus iota by 2, 0, 0, E1, 0, 0, E2, E1, E2, 0. So this is the vector contribution of EIJV. Now let us look at the remaining part of EIJ, which is EIJT. For the tensor part, let us see what is the constraint. One constraint is that it is traceless, and another constraint is that which we have imposed, that it should be traverse. Okay, so let us use this traverse constraint. Let us see what we get from this transverse constraint. From the transverse constraint, we can write this as, okay, let us see, this is delta I K E T I J comma K, right? E T I J comma K, and E T I J comma K. So in the Fourier space, this would become delta I K, and then KK component, K component, iota here will come, then ET IJ comma K. Is that right? Sorry, ETIJ. Right? Right. Now this becomes this in Fourier space, and out of this only K3 component will survive. So which means that when we contract this on K, we will be left with the because other components are 0, so we will be having delta I 3, right? Okay, delta I 3 and K 3. Is it making sense here or not? ETIJ I3 K3. Let's see. ETIJ. We are going to say that K, but K only 3 survives. So KI3, K3, ETIJ, and from here only I equal to 3 survives. What is K3? Yes, K3 is K. K3 is K, and I. Okay, so let's see first. This will be K3 is K, I, K, delta I3, ETIJ, right? So when you contract this on J or I, you will get ET3J. ET3J. Yeah. So we get ET3J. ET3J delta. Yeah. So you contract this and you will get IK ET3J is equal to 0. So we will have because this is equal to 0, transverse condition constraint. So this is equal to 0, and therefore ET3J is equal to 0. And what does this mean? This means that if you write ET components, you have ET11 component. What about one second. So we have ET11 component, we have ET12 component. We cannot have ET13 component because this is going to give us ET31, ET31, ET13, ET23, ET33, and ET32 components. They will all be 0. So this is 0. And then let's write the 0 components first. ET31 is 0. Third row, first column, 1, 3, 2, 3. Second row, third column. Third row, third column. Third row, second column. Right. So all these components are 0 because of this constraint. And we have ET11, we have ET12. And because of this is also ET12 because it is the metric is symmetrical. So I can write this also as same, like instead of 2, 1, I can call it 1, 2 because they are symmetric. And ET11 is now I have to make this traceless also. In order to make this traceless, I will write this as ET minus ET11. So this is my ETIJ. Now I have, what do I have? I have A, I have B, I have D. One second. I have, let's start again. I have A, I have D, and B and okay, B I get from BS, and E I get from ESIJ. These are 4 scalars. These are 4 scalars. Then I have 2 vectors. What are the 2 vectors? I have B vector, and then I have E vector, which I get from EIJ vector. Then I have one tensor, and that tensor is what is that tensor? It is ETIJ. And I have seen that how these perturbations look in the Fourier space. So now let us write the perturbed metric in the Fourier space. So we are going to write now the perturbed metric delta G mu nu in the Fourier space. Let's write delta G mu nu in the Fourier space. Delta G mu nu, which is basically a square h mu nu. I'm going to split h mu nu now into the contribution that comes from the scalar components plus the contribution that comes from the vector components plus the contribution that comes from the tensor components. So I have split this h mu nu perturbation into 3 parts. So now let us write the scalar part first. What is h mu nu scalar? H mu nu scalar is we have a, what is it? We have minus 2a minus bi, so we have minus 2a and then minus bi. Minus bi means minus bi scalar, and then I have minus bi scalar, and then we have hij scalar. Hij scalar is minus 2d delta ij, plus 2eij scalar. This is what we have. Okay, now I'm talking of the scalar components of h mu nu. So this is minus 2a 0 0 minus iota b, right? That's what we saw, that bis is iota b. Bs is minus iota b. So we got minus iota b. Now next this is minus this is 0 0 minus iota b. Sorry, this is minus sign, so this will be plus iota b. This is plus and this is plus. Then we have this is done. Now next is we have component here minus 2d plus 2eij scalar. What is eij scalar? Eij scalar is e by 3 minus 2e by 3. So we have e by 3 and 0 0 0 minus 2d plus 2e by 3 and then 0 and then 0 then 0. Then we have minus 2d and minus 4 e by 3. This is the scalar part of h mu nu. Scalar part of h mu nu. Now let us look at the vector part of H mu nu. Vector part. Vector part of H mu nu is we have this is 0 and this will be here, it will be vector minus this is 0 and this is minus bi vector minus bi vector and then plus 2eij vector 2eij vector. So what is bi vector? B1v, B2v. So we get okay. Then what is eij vector? Eij vector is this minus iota e1 by 2 minus iota e2 by 2. Okay, minus iota e1 by 2, two components 0, minus iota e1 by 2 minus iota e2 by 2, 0. Right, so these are the vector components. Now let us look at the tensor components. ET11, ET12. ET11, ET12, ET12 minus ET11. Sorry, I made a mistake here. We need to multiply this vector component by 2. So that means this will be this. And here so here again we have 2eij. Yes, so this will be 2 here. 2, 2, 2, and 2. So we can write delta G mu nu scalar. Delta G mu nu scalar will be this thing multiplied by a square in front. So I can say delta G mu delta G mu nu scalar is equal to this a square here, a square, and delta G mu nu vector is delta G mu nu vector is equal to this. Right. And delta G mu nu tensor is equal to this. So by decomposing a vector into scalar and vector, a tensor into scalar, vector and tensor, we have been able to separate the three modes as you have seen in this video, so that the three modes are now delta G mu nu s and delta G mu nu vector and delta G mu nu tensor. They are these three modes are separated from each other. They are three separate tensors, and in the evolution of delta G mu nu, these three modes they evolve independently. Therefore, when studying perturbations of one type, for example, when we are studying the perturbations which are scalar, we can completely ignore the vector perturbations and tensor perturbations as if they are not present. And when we are studying the tensor perturbations, we can completely ignore scalar and vector perturbations. So all these three modes are decoupled from each other. And yeah, so that is the elegance of this separation, which we clearly see when we align the z-axis along the k in this k mode, and then we see that they are nicely separated. So the here in this delta G mu nu s matrix, you can see that there is no contribution coming from the vector part, and so scalar, vector and tensor modes are separated. And we will talk more about this separation when we look at Einstein equations. In Dodelson's textbook Modern Cosmology, I have found one section called the decomposition theorem, where Dodelson gives us one exercise in order to prove that scalar and tensor modes they are separated from each other. Again, if the time permits, and if based upon my other priorities, if I get time, I will come back to it in more detail. We would like to see this separation in more detail, and for now I think what we have covered so far is good enough for us to make further progress in understanding the scalar perturbations, which is the main goal for now. But then we'll come back to tensor perturbations also, and we will come back to this question again, that how come these modes are separated from each other. because when we say separation, we mean that there is no interference from the other modes. Yeah. So, okay. Thank you.